Hi, in this video lecture we're going to talk about matching two data sets using people's names. So the situation that we're in is that we need to join two data sets, but we do not have unique identifiers. What we've got going on is that there's no ID variables, or at least no ID variables that match on these two data sets, and we need to combine them for the project that we're working on. Now, this is a situation that we do not want to be in as data scientists. We want to use unique identifying fields of data, ID numbers, put them together, get things to work out beautifully like that. But that doesn't always work out. What I want to do, I want to talk about what you do in this bad situation to get the best result possible. So what we're going to do, we're going to use string distance matching on people's names. So here's the idea. I've got two data sets, and I've got people's names from both the data sets. Now, if the names match up perfectly, it's really not an issue as long as we don't have duplicates. Well, what comes up more frequently is that one person will have, they'll put down Elizabeth, and it will be that way in one record. In the other one, it's Beth. It might be, there might be a Mike in one data set and Michael in the other, and it's the same person, and we need to match them together. So what we want to be able to do, we want to get the names to match up, even though they don't necessarily match up exactly as printed as a character string. Okay, so where do these problems come up from? So just so that we understand why these are issues, and these are the issues that I deal with the most. These are actually the ones that come up the most often in order, top to bottom, for me in my work. So a lot of times people go by a nickname or a middle name, very common. Last names being changed. That's either they get married or they get divorced. Usually it's women. In my work, it's almost always women that are getting married for this. But usually I have a human resources record on, there being an update on their status, so that this isn't too much of an issue for me personally. But if I didn't have that human resources data set, it would be. Now, something that is another issue that comes up: inconsistent selection of last name when someone has a hyphenated last name. So if their last name is Smith Williams, they might put down Smith, they might put down Williams, they might put down Smith Williams, they might put down Williams Smith. And people are inconsistent about this. It's their name. They can do what they want with it. It's fine. We just have to deal with it as data scientists. One that really surprised me, I did not expect this one to happen. Inconsistent spelling of first names. I didn't think that would be the case, but I come across it in my work. Another one is if a person has an apostrophe in their name, people tend to be inconsistent about including punctuations in their names. Whether that's like an O'Neill or they have an apostrophe in their first name, something like that. And another issue that comes up, and I've only seen this there's only been an issue for me with twins, and this is a problem I have not fully been able to solve without manually checking stuff. When I'm dealing with twins, a lot of times the parents will give them very similar names, and so if I'm looking quick, I'll conclude they're the same person. All right, so what I want to talk about now is what are the best practices when we're in this uncomfortable situation. So first and foremost, when you are done, you need to double check your output to make sure that you're getting what you want to get. That's very important. You need to do some quality assurances, quality control checks. Have your secretary work on that. Whatever it is, just make sure you do it. If you have too many records to check, spot check a few. Do your best. Now, what I found that works the best in most situations is I'll make a character string that has the first, then the middle, then the last, then any appendage that they have, such as junior, senior, second, third, whatever like that. If I don't have their full middle name, I'll put just their middle initial. And I find that this is the best way to go. So why do I do this? Well, if someone has the name of John Robert Smith, let's say, and they go by Robert Smith, if I have the middle name in there on their full name, then when they go by Robert Smith in the other record, it's going to be easier to match up on the two. And if I have John R. Smith on the other record, now I'll be able to match up on that also. So I go with all these, put them all together. Appendages tend to be like rarer in data sets, and they also tend to be very inconsistent on being recorded when they are present. So you might want to drop that one. You'll have to basically do some test cases to see if that works for your data. Now, this one is a big one. This one is my trick to solving this and dealing with this is what I will do is I don't match on the entire data set. I partition on another variable that is almost never where there's almost never an error. I find that my work date of birth is almost always correct. It's not always correct, but very consistently it's reliable. So what I will do if I need to match on names, I'll partition the data by birthday if I have it, and then I'll look for matching birthdays, and then I'll do matching names with string distance, and this works very well. Now realize that this is the situation where we don't have perfect matches. If I had perfect matches and I did not have duplicates, I wouldn't have to worry about all this junk. Now, something that I have found that is a good idea is to go ahead and remove all punctuations from people's names before you start doing the string distance matching. So remove the apostrophes, remove the hyphens. I haven't decided if replacing with a space or just pulling them out and not putting a space there is best. I haven't come to a conclusion on which one is better, but you can give it a try if you get into this position. I've tried it both ways. It honestly gave me about the same results. Something that you're going to want to do is when you write your code, you're going to have to make choices on how you execute and on which parameters you're going to do, what your penalty terms are going to be, if you're going to use qgrams, what q is equal to, what distance metrics you're going to try, things like that. I strongly recommend that you try it on known cases first and check the accuracy before you commit to it, because we're in the situation where we will never truly know if we're right or wrong when we do this type of matching. We're just hoping that it works out to be correct. Now, the last piece of advice I have for you is that when you do this matching, what I would like to do is I'll take a really restrictive method of matching, so like it has to be perfectly equal and birthdays are equal, and then I'll lighten up a little bit. So then I'll go with Hamming distance. They don't have to be exactly equal if they're within a certain Hamming distance, but the birthdays have to be the same. And then I'll go the longest common substring for the ones that haven't gotten picked up by a match. And then if the longest common substring is within a certain tolerance level, then I call that a match and I pull those records off. Now for the ones that don't have a record so far matching up, then I go to the LV distance metric and repeat. I keep on doing this over and over and over. So remember that these are the DIST, the delete, insert, substitution, and transposition metrics, and they get there are more operations in the ones over here and fewer here. And if you're going to use the JW distance metric, you can decrease your penalty term. Remember, it goes from 0 to 0.25. Start with one value and then keep on progressing it up. All right, so for this, what makes a case study is that you actually go and you try it out on some data set. Well, what I'm going to do, I'm going to generate some fake data, and I'm going to make up the scenario where we have one set of names, another set of names, and they're supposed to match with each other. And I don't know which ones match. Now, in this scenario, there are no perfect matches by how I built the data set, because I'm trying to demonstrate the string distance aspect of it. But what I would start out doing, if this was a real data set, I would go with perfect matches and that have also the same birthday. And then I would go on to the other techniques. So let's go ahead and let's load the data. The sample will come from the nicknames data set that I got from GitHub, and the 2010 U.S. Census last name data that I got from Data World. And the one thing that's nice about the U.S. Census data, it's only 1,000 names. It's the top 1,000, and it has the frequency of them. So for last names, last name frequency will be proportional to the U.S. Census. All right, so we're in the scenario where what I'm going to call name 1 is their proper name, and what I call name 2 is using a nickname for their first name, but last names are going to match every single time on this. And let's go ahead and load the data. Let's take a look at our nickname data set. All right, so here's the name, and here's the nickname. Now, notice that I put everything in lowercase. By putting everything in lowercase, I'm going to be consistent for different spellings. If sometimes in a record, maybe someone put their entire name lowercase, maybe they put everything uppercase, maybe they did it proper case. You don't know. Put the lowercase because usually they're focused on the letters, not the case in people's names. There are some weird exceptions to that, but it's not worth worrying about. Now, for the last names data set, this is coming from the U.S. Census, top 1,000 names. And I trimmed out everything that we're not going to use on this. So we have the family name, and my name's coming up top. Hey! And then here's the frequency count. And this is the top 1,000 surnames in the 2010 U.S. Census. I thought Hernandez and Martinez were higher up, but I guess I was wrong. Now, for the case study, we're going to generate some data so that we have something to look at, something to give us a concrete evidence of this working, and so we can get a feel for how this actually works. The situation that this is going to create is actually worse than any situation I've encountered professionally, but I think this is a good way to go. If you're going to run this code on your own, you're going to want to probably reduce the number of observations. On my work machine, when I put 5 here, it took too long to run, and my work machine's a beast. You might want to reduce this down to 3 if you're going to do it. And if you want to see repeatedly how things work out, change the seed number. I've always put 823 because that's UCF on a telephone. All right, so what I'm going to do, I'm going to use pseudo random sampling. So names and nicknames are going to be uniformly sampled. So I'm going to come up to this data set, and I'm going to uniformly pick a row. So I'm uniformly picking on their proper first name, not on their nickname. You'll notice that AB is going to come up more frequently. It will be disproportionately frequent compared to other nicknames because it appears so many times. But that's okay for this example. Last names are going to be sampled with the probability of being selected proportional to these counts. And for date of birth, uniform random sampling throughout the 90s. So here we're going through and we are selecting rows. I'm using the sample integer function to randomly pick rows from the nicknames data set. And then I am going to use the sample function to pseudo randomly pick last names. And you notice that for prob, I'm setting it to the frequency count. Notice that this vector frequency count is a count vector. R automatically takes care of making it of rescaling it to be a probability. And now for DOB, that's date of birth, we're going to go through and we're going to uniformly sample from 7,305 to 10,956. Why am I picking those numbers? All right, well, dates are stored in R as integers, and the origin is 1970, January 1st. That's either 0 or 1. I can't remember which one it is, but if you put in as date and you put in a number, and you put in 0 or 1, you're going to get one of these numbers. If you put 7,305 and you put it in as, you convert it to as date with, this is the origin, this is the default origin in R, by the way, then this is going to put January 1st of 1990. This is going to be New Year's Eve of 1999. And we are, since I'm using the sample function and I'm not specifying the probability, I'm doing uniform discrete pseudo-random sampling. Now, after this, I have the names, I have last names, I have nicknames, I have names in the data set. So what we're going to do is we're going to paste them together. So name 1 is their proper name, name 2 is their nickname, and what we're going to want to do is, given the nickname, I want to identify what their proper name is as correctly as possible. Now, this is a task that we probably will not be perfectly accurate for. So remember, when I'm done with this, if this is real life, I have to be very careful in this process, and I have to double check my work, like line by line. It's loads of fun, let me tell you. All right, so what I want to do now is I want to do the string matching without using date of birth. So I want you to see how awful the results are going to be, because I've got thousands upon thousands of records in this data set. My M is 10 to the 4th. So that's, a good number of names floating around. When I match, if I don't restrict it by date of birth, what's going to end up happening, I'm going to get terrible, terrible results. Now, something I do when I do this matching, I set max distance to infinite because I want you guys to see how the individual metrics match up. If I was doing this in real life, I would not use infinite. I would definitely restrict it down. What this is going to do with infinite, this is going to find a name somewhere, someplace, some way, some shape, some form. It's going to find the one that it thinks is the best to match. This is not a good practice, but I want you to see this output to get an intuition on how the functions behave. Now, one thing about this, if I have ties in the matching, it's going to pick the first one. It's only going to give me one of them. It's not, so if there were 5 that all have the equal distances, string distance, it's not going to tell me which, what the 5 are. It's going to tell me just which one is the first one as it appears in the data set. Oh, and something I want to point out, I'm using the amatch function from the string dist package. And normally I try not to teach with special functions, because special functions disappear the moment you quit taking the class. I don't like it when instructors use special functions, and what I'm doing, I find it makes the code harder to follow, harder to reproduce. I'd rather just use the base functions as is, but because of how long the output or how the statements were becoming, they were too wide for the paper, I went ahead and made a custom function. If you replace this custom match aspect with this part, you can make it so that there is not you have to modify it a little bit. You can make it so that there is not a special function going along. All right, so now I want to go through and I want to do the matching. I want to show what is it like, what was the output going to be like if I match with each string distance function. So the first column is their proper name. This is what I want to have as output. Second column is the nickname. This is the nickname that I am using to find the closest proper name. Now, when I'm doing my matching, this column is going to be when I'm using the Hamming metric, so that I do substitutions, and then longest common substring, which is equivalent to delete and insert. Then the LV metric, which is delete, insert, substitute. Then the optimal string alignment is delete, insert, substitute, and transposition once. And this one, the DL, is delete, insert, substitute, and transposition as many times as needed to get what we want. Now, qgrams looks at substrings. Cosine is a generalization of correlation. It's taking the angle between two vectors generated by the qgrams algorithm. Jacquard is based off of qgrams. Then we have a JW. This is a penalized system, and SoundX is based off of phonics. All of these have advantages and disadvantages depending on your situation. And I put the strings as factors because R is stupid and always makes, by default, a lot of functions make strings into factors, which does not make sense for this problem. All right, so let's take a look at what happens when I match it. And I'm only going to look at the dist function, the dist matches. And so here is what we should have gotten. And here, if I just take the name straight and raw and just dive right in, here's what we get every single time. Well, this is not encouraging because Elizabeth matched up with Jeff, then Elizabeth. That's okay. All right, that's good. Winfred Reynolds. Let's see. Oh, it's wrong every single time. Geraldine Jordan. Wow, that's a heck of a name. Edith, Jerry, Goodman. Yeah, see, these are all off. Rosabelle Friedman. And let's see. Oh, got it right on these 4. And then Margaretta Campbell. Missed it every single time. So we can see that the Hamming distance really isn't working out too well. Hamming doesn't work well when you put the infinite criteria on there. So what's it basically doing, it's going to look for the fewest number of substitutions, and it's going to restrict itself down to the core names and proper, or nicknames and proper names that have the same number of letters. That's what's most important for the Hamming distance. Otherwise, it gives infinite. So what this is really doing is this is really just looking for the same number of characters if it can find it. Oh, and Ann Madden, let's see. Oh, Ann Madden on these. All right, so far we're looking like these are the best ones to work with. All right, now let's go ahead and let's try to count how many times it's correct, how many times it's incorrect. So I go ahead and I use an S-apply statement. You notice I've got equal sign and not equal in here, and I'm adding up all the times it's incorrect. And if I look through here, so let's see, what, 63%, you know, it's, what, 6% of the time it's correct. 54, 41, 41, 41, 30, 38, 27, 40, and fraction of a percent. Yeah, didn't work out too well. So best one was longest common substring. If I had to do this, I would use that one, but really is not the best way to go. Really, longest common substring, that's going to be matching on, you know, because of this data set, the last names are always correct. And because of that, you know, when it's correct, it's picking up the last name and then it's matching on the last few characters of the first name, since it's longest common substring. Not the best way to go, but you know, at least we know, at least we can quantify how bad it is. So this is awful. We don't want to do this unless we want to get fired. And if we want to get fired, we can just get fired in a much more interesting way than being a screw up. All right, so here's the idea. I'm going to go through, I'm going to partition the data set by birthday. Now, when I partition the data set by birthday, then that's going to greatly reduce it down. I'm making the assumption that birthday is always correct in this data set, and that's a good, reliable one to go with. So what I'm going to do, I'm going to use the split function in R. So what split does, it takes a data set, and it takes a vector, and then by the levels of the vector, it makes a list, and it's going to make a sub data set where each of the sub data sets have the same value for this vector down here. And here's the output of it. So here in this fake data set, we have 2 observations for people that were born on New Year's Day, and then 2 observations when they were born the day after New Year's Day, and so on. And I can keep going down the list. All right, so now I modified my custom matching function. Once again, I hate custom functions. For teaching, I use them in work, but for teaching, I find them to be more difficult for students. And I'm using infinite for max distance. I would not do this in real life. I want to show you the output. I would restrict this down to something that I felt was reasonable, maybe like 3 to 5 for the dist functions, maybe something like that. And we're going to go ahead and match on this. All right, so what I'm going to do, I'm going to make a list. I'm going to check it twice. to find out who's naughty and nice. In this list, I'm going to go through and I'm going to match the data coming from here, just like I did with the previous one, but the previous one was the big data set. Here I'm going to match on the smaller ones that have a lot fewer observations. And since I have fewer observations and I know they have the correct birthday, or I believe they have the correct birthday, then I'm very confident that what I'm going to get is usually going to be correct. And this is pretty much the same as the code from above. It's just that now I put it inside a for loop where I go across the loops. And here, remember that the names are the unique birthdays in the random sampling. Now, after I match them all up, so they're in a list. I put them into a dplyr bind rows statement to make them into one data set. All right, so now let's take a look. Let's see what the output looks like. Okay, so when I have Carol Brown, Hamming gave me nothing, and then correct. That's good. All right. Ed Garrett, nothing. Correct. All right, that's good. Wilfred Dixon, missing. Then correct. Maddie Gomez, correct across the board. Lawrence Jordan. Oh, Hamming dropped the ball on this one. Gilbert Wall. Okay, so that is interesting. I thought it would have been correct. But Lawrence Jordan, everything's good across the otherwise. Now Gilbert Wall, everything's looking good. All right, so now let's take a look. How are we doing on correct and incorrect? All right, so Hamming was, so notice that when I have an NA, like these aren't going to add up to the same numbers I have over here when I add them up because of all the NAs in there. Number of times of correct, number of times incorrect. But if I look through, this is, less than 2% error. This is, or less than 1%. So these are pretty good numbers. They're not perfect. Like remember that, these 15 records, if I need to have 100% accuracy, those 15 in real life, I wouldn't know which 15 are wrong. So I would have to go through and try to match them up. That's a huge improvement. Now, if I had a larger data set or if I had more overlapping birthdays, so like for me at work, usually, usually birthdays range over 5 years for what I've been doing for my stuff, maybe 6. And so if I would put more birthdays, or I would put the birthdays over a smaller range, there would have been more overlap, and we probably would have had more error. But I hope that this convinces you that this partitioning technique is a good way to get around having to join data sets when you don't have ID numbers. I hope you're staying healthy. I hope you have a great weekend.